Good day everyone, today we shall be discussing inverse of modular arithmetics. From this example, supposing we are to find the inverse of 2 in modulo 7. It is important to note that the inverse of x is a number, say x prime, that multiply x in both ways, whether multiply s or x multiplies it and give 1, meaning it could be x prime multiplied by x and it gives 1. With this, if we are to find what this x prime is, it will be equal to 1 all over x. And since what we are dealing with is integers, in modular arithmetic we deal with integers, not fraction. So if this inverse do exist indeed, then it will definitely be an integer inside this modular set. So in this case, due to that reason, we denote this 1 all over x as x raised to power minus 1. So that is the inverse of x. And that is the reason the value we are looking for here is the inverse of 2. Not 2, but inverse of 2. It's another element inside this modular arithmetic, modulo 7, that is the inverse of 2. With the definition we've just gotten, so if I should say, let this inverse of 2 to be equal to x, it means we are looking for a number that we multiply 2, which is x, that we multiply 2 to give me 1 modulo 7. I hope that is clear. Let's denote it with x prime for better understanding. Now to solve this now, our intention is to make x prime subject of the formula and not having fraction at this other side too. And since we are dealing with modulo 7, so we can easily solve this. So we need to find by multiplication a number. We need to turn this to a number or a multiple closer to the modulo we are dealing with, which is modulo 7. If we should use 3 is lesser than 7, so preferably something bigger than 7. So if you use 3 here, it will be 6. That is 6x prime, which is lesser than 7. Preferably we use something bigger. So let's go for 4, which is 4 times this. 2x prime will be equal to 4 modulo 7. So with this, I have 8x prime equal to 4 modulo 7. But 8x prime now can as well be written as 7x prime plus x prime, which is equal to now 4 modulo 7. So this, since it's a multiple of 7, becomes 0, then I'll be getting x prime equal to 4 modulo 7. Therefore, this is the inverse of 2 in modulo 7. So the inverse of 2 raised to power minus 1 modulo 7, that is the inverse of 2 in modulo 7, is equal to 4 modulo 7. I hope that's very clear. Using this same method again, we can get the inverse of 3 in modulo 7. So this is going to be 3x prime equal to 1 modulo 7. For e is 15. We can easily get 15. That if we multiply this one by 5, this will be 15x prime is equal to 5 modulo 7. And this is 14 plus x prime, which is 14 x prime plus x prime is equal to 5 modulo 7. Here, this becomes 0, and this is x prime now is equal to 5 modulo 7, which implies that the inverse of 3 in modulo 7 is equal to 5 modulo 7. Since inverse of every number is unique in this case, then it implies that what the inverse of 4 is going to be 2, and the inverse of 5 is also going to be 3. Also, if we keep on with this method, you will realize that what the inverse of 1 is 1 itself. The inverse of 6, which is the last number in the modular system of 7, is 6 itself. Just like modulo 7, all elements in modulo 3, 5, 11, 13, and all other prime numbers that are modulo, if we have them to be a modulo, all the elements in them always have inverses, except 0. Let's consider modulo 4. Take for instance in modulo 4, the inverse of 2 in modulo 4. You would realize that if you can't, there's no how you keep on multiplying the value we've gotten here. Supposing we say this is 2x prime equal to 1 modulo 4. There's no value you will multiply with this value here that will give you at the end of the day, when you reduce it, that will give you 1 at the end of the day. You would realize that what 2 has no inverse in modulo 4, so it has no inverse. Modulo 3 inverse, of course, does. We have that of 3. If we rewrite this one implies 3x prime is equal to 1 modulo 4. And to go on with this, multiply by 3, this will give me 9x prime is equal to 3. Then this becomes 8x prime plus x prime is equal to 3 modulo 4. Then you realize that our x prime now is equal to 3 modulo 4. Since this is a multiple of 4, it becomes 0. So here we realize that what the inverse of 3 is equal to 3 itself modulo 4. Also in this case, 1 is inverse of itself, but we already realized that what 2 is the only element in modulo 4 that has no inverse. Considering modulo 6 now, you would realize that 1 inverse of 1 is also 1, but 2 has no inverse. So this doesn't exist. 3 inverse as well doesn't exist. Likewise, 4 inverse doesn't exist. But that of 5, which is 5 prime, 5x prime equal to 1 modulo 6. If we multiply through by 5, this will be 25x prime is equal to 5 modulo 6. And then you also notice that this is 24 plus x prime, so this is x prime is equal to 5 modulo 6. So here, inverse of 5 here is equal to 5 modulo 6. I hope that is very clear. With this, we can deduce that any number that shares a factor with a modulo or is a factor of the modulo itself has no inverse in that modulo. Just like 2 and 3 are factors of 6. However, 4 shares factor with factor 2 with 6. So due to that reason, it has no inverse in modulo 6. So are the cases of other modulos we came about. If they share factor with any of their elements, that particular element will have no inverse in them. So right now, every element x except that is equal to 0 in modulo n has inverse if n is prime. So in that other case, we mean that what if the GCD of that element and the modulo itself n is equal to 1, meaning it's either they are primes or they are co-primes or they are relatively primes. We have also seen that if n is a composite, any number that shares a factor with it has no inverse. That will be all for now. Please join me in the next video. I shall be using a less brain tasking method to compute the inverse of large numbers in large modulo. Please hit the subscription button if you haven't yet, like this video, and of course, class. Bye for now.